Energy has never been the problem. That's the first thing most people get wrong. The universe is overflowing with energy. Sunlight hitting Earth every second, chemical energy locked in fuels, electrical energy flowing through grids, even thermal energy dissipating into the atmosphere. The real question has never been whether energy exists. The real question is, why is it so hard to use it efficiently, reliably, and profitably? And the answer is not found in policy, hype, or even technology alone. It is buried in something far more unforgiving, something that does not negotiate, does not adapt, and does not care about investor sentiment. The answer is physics. More specifically, a small set of universal laws that quietly dictate which energy systems succeed, which ones fail, and why so many promising ideas collapse before they ever reach scale. Let's start with the most fundamental constraint, the conservation of energy. This law sounds simple, almost trivial. Energy cannot be created or destroyed. It can only change form. But hidden inside that simplicity is a brutal implication. Every time we try to convert energy, from sunlight to electricity, from electricity to hydrogen, from hydrogen back to power, we are not creating value out of nothing. We are simply reshaping energy, and every reshaping step introduces losses. This is where the illusion of infinite clean energy begins to break down. Because while energy itself is conserved, useful energy is not. Every conversion step leaks value, and those leaks accumulate across the system. Now layer on top of that the second law of thermodynamics, and the picture becomes even more unforgiving. This law tells us that entropy, the measure of disorder, always increases. In practical terms, it means that every energy system becomes less efficient as it operates. Heat is lost. Friction builds. Irreversibility creeps in. You can never get back exactly what you put in. And this is where the entire clean energy conversation starts to collide with reality. Because while we can design better technologies, we cannot design our way around entropy. We can only manage it, minimize it, and price it into the system. This is exactly why hydrogen, despite all its promise, sits at the center of such a difficult economic equation. On paper, hydrogen looks like the perfect energy carrier. It can store energy, transport it, and release it without carbon emissions. But when you follow the molecule through the system, from electrolysis to compression, storage, transport, and finally conversion back to electricity, you start to see the cumulative effect of thermodynamic losses. Each step chips away at the original energy input. And by the time you reach the end of the chain, you may only retain a fraction of what you started with. This is not a technology failure. This is physics doing exactly what it has always done. And this is where most narratives begin to diverge from reality. Because when people talk about scaling hydrogen, they often focus on the electrolyzer, the headline technology. But the real system is far larger. It includes compressors, pipelines, storage tanks, cooling systems, power electronics, and integration with the grid. All of these components exist within the constraints of thermodynamics. All of them consume energy, all of them introduce losses, and none of them can escape the second law. So when a project claims a certain efficiency or cost target, the real question is not whether the electrolyzer can achieve it. The real question is whether the entire system can sustain it under real-world conditions. Now let's go deeper into how energy actually moves through these systems. Because energy does not just sit still. It flows, it transfers, and it interacts with matter through forces. This is where Maxwell's equations come into play. These equations govern electricity, magnetism, and electromagnetic waves. They are the reason electrons move through wires, the reason power can be transmitted across grids, and the reason electrolysis works in the first place. When you split water into hydrogen and oxygen, you are not just applying energy. You are manipulating electric fields, charge distributions, and molecular interactions at a fundamental level. But here's the catch. These interactions are not perfectly efficient. Resistance in wires generates heat. Power electronics introduce switching losses. Even the act of moving electrons through a circuit comes with energy penalties. And as systems scale, these small inefficiencies compound. A few percentage points lost in one component may seem insignificant, but across an entire hydrogen production and distribution network, those losses can define the difference between a viable project and a stranded asset. Now, step back and consider motion itself. Because energy systems are not static. Fluids move through pipes, gases are compressed and expanded, mechanical components rotate and vibrate. All of this is governed by Newton's laws of motion. These laws describe how forces interact with mass to produce motion. They explain why compressors require energy to increase pressure, why pumps consume power to move fluids, and why mechanical systems experience wear over time. And again, the implications are not just theoretical. Every time you compress hydrogen, you are doing work against physical forces. That work requires energy, and that energy is subject to thermodynamic losses. Compression is not free, storage is not free, transport is not free. And when you begin to map these costs across a full-scale hydrogen infrastructure, you start to see why so many projects struggle to reach final investment decision. It's not that the technology doesn't exist, it's that the physics imposes a cost structure that is very difficult to overcome. Then there is gravity, described by the general relativity in its most complete form. While gravity may seem less relevant to energy systems, it plays a subtle but important role. It influences fluid flow, pressure gradients, and the design of large-scale infrastructure. It affects how energy is stored, especially in systems like pumped hydro, and at a broader level, it reminds us that energy systems are embedded within physical environments that impose constraints of their own. You cannot design an energy system in isolation. You have to design it within the context of the world it operates in. Now let's zoom into the smallest scale, where quantum mechanics takes over. At this level, governed by quantum mechanics, the behavior of particles becomes probabilistic. Electrons do not move in neat, predictable paths. They exist in probability distributions. Chemical reactions depend on energy states, activation barriers, and quantum interactions. And this is directly relevant to technologies like electrolysis and fuel cells. Because the efficiency of these systems depends on how easily electrons can move, how reactions occur at electrode surfaces, and how materials behave at the atomic level, this is where breakthroughs are often claimed. New catalysts, new membranes, new materials that promise higher efficiency or lower cost. And while these innovations can shift the boundaries, they do not eliminate the underlying constraints. Quantum mechanics may allow us to optimize reactions, but it does not allow us to bypass thermodynamics. The two are deeply connected. One governs the microscopic behavior of particles, the other governs the macroscopic flow of energy. And together they define the limits of what is possible. Now bring all of this together and you start to see the real system. Energy enters the system, governed by conservation laws. It is transformed through processes constrained by thermodynamics. It moves through infrastructure governed by electromagnetism and mechanics. It interacts with materials governed by quantum physics. And at every step, losses accumulate. Constraints stack, costs emerge. This is the hidden machine behind every energy technology. And it is why so many projects look viable on paper, but struggle in reality. Because paper models often assume ideal conditions, perfect efficiencies, stable operation, predictable inputs. But real systems operate under stress. Variable renewable energy, intermittent demand, equipment degradation, regulatory constraints, financing pressures. And when these real-world factors collide with the underlying laws of physics, the system is pushed to its limits. This is where the conversation shifts from technology to survivability, because not all energy systems fail equally. Some are more resilient than others. Some can absorb inefficiencies and still operate profitably. Others collapse under the weight of their own complexity. And this is where a new lens becomes critical. The idea of evaluating systems not by their theoretical potential, but by their ability to survive under stress. If electricity prices fluctuate, can the system maintain utilization? If capital costs rise, can the project still achieve acceptable returns? If efficiency drops slightly, does the entire business model break? These are not engineering questions alone, they are system questions, and they are rooted in physics. Because physics does not just define what is possible, it defines what is sustainable. It defines which systems can operate reliably over time, under real conditions with real constraints. And this is where the gap between hype and reality becomes most visible. Take green hydrogen again. The narrative often focuses on cost targets, $2 per kilogram, for example. But that number is not just a function of technology. It is a function of physics, economics, and system integration. It depends on electricity prices, electrolyzer efficiency, utilization rates, infrastructure costs, and more. And each of these factors is influenced by the laws we've discussed. You cannot simply declare a cost target and expect the system to conform. The system must be designed to achieve it within the constraints of reality. And this is where most failures occur. Not because the technology is flawed, but because the system is incomplete. Because the assumptions do not hold. Because the physics was underestimated. Because the integration challenges were ignored. And because the economic model did not fully account for the losses, the variability, and the complexity of the real world. So what does this mean for the future of energy? It means that success will not come from ignoring these laws, but from designing systems that work with them. Systems that minimize losses, optimize flows, and balance trade-offs. Systems that are robust, flexible, and grounded in reality. And perhaps most importantly, systems that are evaluated not just on their potential, but on their ability to survive. Because in the end, the laws of physics are not barriers, they are filters. They separate what can scale from what cannot. They determine which ideas move from concept to reality, and which remain trapped in presentations and prototypes. And they do so quietly, consistently, and without exception. Energy cannot be created or destroyed. Entropy will always increase. Forces will always act. Particles will always behave according to their fundamental rules. These are not suggestions, they are the foundation of the universe. And every energy system we build must operate within them. So here's the real question you should be asking, not just as a viewer, but as a developer, investor, or engineer working in this space. If these laws are already defining the outcome, are you actually building within them? Or are you still modeling outside reality? And if you want to go deeper into how these physical constraints translate into real project decisions, how utilization affects cost per kilogram, how system losses reshape financial models, and why so many hydrogen projects stall before a final investment decision, this is exactly what we break down inside H2 Hub by Renee Energy. It's where the conversation moves beyond theory into execution, with tools, frameworks, and system-level thinking designed for people actually building in this space. You can explore it through the link in the description. And if this video changed how you see energy systems, then you already understand the bigger picture. This isn't just about hydrogen, this is about how the world actually works under the surface. So subscribe if you want to keep uncovering these hidden systems, and share this with someone who still thinks energy is just about technology. Because now you know it's about physics, and physics always wins.